Let's take a look at this slicing problem in section 6.3. This is the harder type of slicing problem because it's being rotated about a vertical axis of revolution. This problem would really be done better with the shells technique, but we can do it with slicing because that's what this section wanted us to do. So when I'm looking at this problem here, it says find the volume of the solid generated when the region bounded by y equals 1/4 x cubed, y equals 0, and x equals 4 is revolved about the y-axis. So over here on my work paper, what I did is I tried to sketch out that the region here and rotate it about the y-axis. What I always like to think of is what one arbitrary slice is going to look like rotated. That's what I attempted to draw over here with this portion over here. What I wanted to show is that there's going to be a larger circle that's rotated around, and then each of those larger circles, we're going to have a smaller circle hollowed out of it. This is going to be the washer type of problem. And the volume of an arbitrary washer is going to be the area of the face, which is pi times the larger radius squared minus the smaller radius squared, and then times the thickness of the slice. And the thickness of the slice is going to be a change in y, because however thick we arbitrarily choose to slice it is going to be a change in the y-axis. So now, with all of those things in mind, I needed to come up with formulas for the radius. Now, the outer radius, super easy. The distance from the axis of revolution to the outside portion of our curve is a consistent distance of 4, whether we're rotating from the very beginning or rotating at the end. So you'll see I said R2 is 4. Now, I know R1, the region that we're going to be hollowing out, is the distance from the axis of revolution to the inside curve right there. And I could say, well, okay, that inside curve is your y equals 1/4 x cubed. Of course, we can't call it that because we need to get our equations all in terms of y. So when I had to solve for x, I said, well, okay, I'll multiply by 4 on each side. X cubed is equal to 4y. Therefore, then I can say that I don't know what happened over there. Oh, there we go. Therefore, I can say that the cube root of 4y is equal to x. Now, that is going to form my smaller radius here. That's this distance right here, the cube root of 4y. So then I can say, well, all right, then the volume of one arbitrary slice is going to be pi times the larger radius squared minus the smaller radius squared times the thickness. Larger radius, 4 squared. Smaller radius, I said, well, it's the cube root of 4y. When I square that, that's the same thing as 4y to the 2/3 power. Makes it easier to work with. So I have my pi times this larger radius minus the smaller radius, each of them squared, times their thickness. That's the volume of one arbitrary slice. I use that down here to find the volume of the entire rotated solid. We say the volume of all of this region that's being rotated is just going to be pi on the integral of where these rotations would begin. Well, they're going to begin down here when y is 0 to where that the rotations would end. The rotations will end up here at y equals 16. So I integrate from 0 to 16, larger radius squared here, and then my smaller radius squared I just kept as the group 4y raised to the 2/3. That's going to make it easier to integrate. So now when I do integrate with respect to y, the integral of 16 is 16y. The integral of 4y to the 2/3 power. I said, well, okay, it's a group to the 2/3 power, so when I integrate it, it's going to be that same group to the 5/3 power, since the inside function is linear, I can use the reverse chain rule and say, okay, not only do I have to divide by that new exponent of 5/3 down here, I also have to divide by the derivative of the inside, 4. Now, that's going to be the correct integral for this function. I need to now evaluate it from 0 to 16. When I plugged in a 16, I had 16 times 16. That's where I got my 256. And you'll see in this second term, I went ahead and simplified it down just a bit. I was dividing by 20 over 3. That's the same thing as multiplying by 3 over 20. So then when I plugged a 16 into that, 4 times 16 is 64. Then I had the cube root of 64, took me back to 4. Well, then 4 to the 5th power was 1,024. And then 1,024 times 3 over 20 ended up giving me this 768 over 5. When we evaluate at 0, both terms are 0, so the lower limit of integration doesn't amount to anything. Both of these are just from the upper. When I went to my calculator and said 256 minus 768 over 5, we got the 512 over 5. And of course, don't forget to multiply by pi, and we get to our final answer there.